We continue by discussing the simulation of reactions on spatially extended systems at the mesoscopic level. So in the previous part, we learned about the formulation of the reaction rate constant from transition state theory, which allows us to calculate the reaction rate from transition state theory and also using mass action law. Now, what if we have more than one reactions? Sometimes these are referred to as reaction channels. So if we have, let's say, events like adsorption, desorption, diffusional hops of species from site to site, and also different types of reactions like this CO oxidation event that I show here, this carboxyl formation event from these two reactants, etc. So if we have many species on the catalytic surface, we have many possible reaction types, and each one will have its own rate constant. So reaction 1 would have RTST, 1 as its rate constant. This is for reaction 2, reaction N, etc. And what I can do is calculate exponentially distributed random times for every one of these reaction events that are possible on the catalytic surface. So this tau1 is an exponentially distributed variable that follows this rate constant, and it gives me the time that the first reaction may happen. And the first reaction may be diffusion of a CO adsorbate from site 58 to site 59. Reaction 2 may be a reaction between that CO and the neighboring oxygen adsorbed atom. So for that reaction, I can use the rate constant that I have calculated from transition state theory. I can calculate the rate, and then I have a random time for that reaction, etc. So out of all of these random times for each one of these reactions, I can take the minimum of them, which will give me the time of the occurrence of the next event. So the time for any event to happen is the minimum out of all of these. And this, there is a mathematical theorem that tells us that this minimum will be an exponentially distributed random variable with rate constant equal to the sum of all of these rate constants. So I can either generate a bunch of random times, take the minimum out of them, or just sum up all the rates, these rates here, also known as propensities, and then generate just one random time, an exponentially distributed random number, which will give me the time of the occurrence of the next event. What is the event that is going to occur? The event with the smallest time, right? The event with the minimum out of all of these times. So and sometimes we say that this is the imminent or most imminent event out of all of them. So I now have a recipe for creating random times of events and then finding which event is going to happen next. This allows us to simulate a sequence of lattice configurations and take samples. So essentially, as I said in my earlier example, what I'm doing is I'm generating random times of the events of adsorption, desorption, diffusion, the different reactions on the surface. I take the minimum, and then I can perform the reaction event on the lattice, so I can update the lattice configuration. Then again, I know the possible reactions that can happen. I can either generate new random times or reuse some random times from previous calculations, and then simulate again the most imminent event that can happen, etc., and so on and so forth. So in the end, after I do this many times, I can simulate this sequence of lattice configurations and take samples that I can then post-process to answer questions like what is the average coverage of an adsorbate, or what is the rate by which some adsorbates get converted into other intermediates, etc. Now, one may be wondering whether there is an equation that governs the statistics of these configurations. So when I say configuration now, I mean the occupancy of the sites in the lattice, right? In the same way as we did with in the previous lecture when we were looking into the statistical mechanics of condensed phase systems, in which we had this one-dimensional lattice with an occupation variable, etc. So when we do the simulation here, we're going to be simulating a sequence of lattice configurations, and the question is what is the equation that governs the statistics of these configurations. Indeed, we can formulate such an equation, and this is called the master equation. So this is the master equation. Let's go through this term by term. So this is the probability of a configuration sigma. So in a very simple lattice in which I have 9 sites, I may be looking into this sigma, this state with this vector of occupancies. In this particular example, I'm only going to deal with just one adsorbate. So each site can have an occupation variable of 0 or 1, and in line with what we have said before, 0 means vacant site, 1 means occupied site. So this sigma bold, again in line with what we have discussed before, represents the state. So if we're looking into this state, there is a probability that I will find my lattice in this particular state or configuration, and this is exactly what this probability stands for, the probability of configuration sigma. Now, the master equation is a balance of probabilities, or balance of probability fluxes, really. So in the right-hand side, I have the influxes and effluxes or outfluxes of probability. And of course, this is an accumulation term. So if I look at state sigma, there will be probability influx terms from other configurations, sigma prime. So for example, if sigma prime is this configuration over here, in which you will notice the 5th site is not occupied, this state contributes to this state with the probability flux, which is the magnitude of which flux is determined by the rate of adsorption on site 5. So probability flows from this state to that state. How fast? This depends on how fast or how frequent adsorption is on site 5. So the state sigma prime is this state here. You see it's almost like this, with the exception of this 0 over here, because this site is empty. So this term would be just one out of the terms that I see here. You will notice that we sum over all the other states, right? So sigma prime not equal to sigma. So this W corresponds to the transition probability from going from state sigma prime to state sigma, and of course this is the probability that we are in that state sigma prime. So the probability that we are here times the transition probability that we go towards state sigma, sum over all states sigma prime. This is the total probability influx, right? All of this with the sum, the total probability influx towards this state from every other state. Of course, in some cases, you may not have an elementary event that connects these two states. For example, if we had the completely empty lattice, this the state sigma prime that corresponds to like all zeros here wouldn't be connected with this state over there. It wouldn't really contribute to flux for this state. Why? Because if we had an empty lattice, then we would have to go through subsequent elementary events of adsorption on site this, on site 5, on site 8 and 4 in order to get to this state. So this W would correspond to elementary events like the adsorption on site 5 that I show here. You will also notice that from this state we may lose probability because of an event which would be the reverse event of this adsorption, right? So desorption from site 5 would give rise to this configuration here. So that's why I have this arrow over there, which models probability efflux to other configurations. So desorption from site 5 would give rise to this. Adsorption on site 9 would give rise to this configuration over here, right? So this would be another example of probability efflux because of an elementary event, in this case adsorption on site 9, which gives rise to this configuration from this configuration. So because of the fact that events are reversible in the micro scale, you will see that we always have these terms coming in pairs. So we will have, for instance, adsorption on site 5 here, but also the reverse event desorption that corresponds to probability efflux from this state to that state, and similarly from this state to this state, or if we have the reverse event of this, desorption from site 9, we can go from this state to this state over here. So this completes the probability balance, right? You can see here we have W, the transition probability to go from state sigma to all the other states when we take into account the sum. So these two terms complete the probability balance. We have the influxes from the other states, the effluxes towards the other states, and all of this is equal to the accumulation of probability in state sigma. Now this, if you think about it, it's a linear equation. It's linear with respect to our unknown, which is the probability, right? So this is the probability here. So we could rewrite this as dp of sigma dt equals a transition matrix, as it's called, a big W times a probability vector p of sigma. So we could try to solve it with sort of standard linear algebra methods like the matrix exponential. However, there is a problem which is typically referred to as the curse of dimensionality. It turns out that the state space in this case is finite because we have a finite number of sites. There is a finite number of combinations of the occupancies, the occupation variables for this finite lattice. However, the state space is so vast, so large, that any computational approach that would try to even store the probability vector and the transition matrix would fail for realistic systems. So if, for example, if n sites is 49, so we have a 7 by 7 two-dimensional finite lattice, and let's say that we had only one adsorbate on the lattice, this would give us two values for the occupation variable, right? 0 unoccupied, 1 occupied. So the number of possible states that we can have is 2 to the n sites, which is already 5.6 times 10 to the 14. Right? So this is quite a large number of possible states, possible configurations. And of course, this is a very small lattice with a very simple system, one adsorbate. This is far from the realistic systems that we would like to deal with in the context of catalysis and surface science, in which we may have tens of species and hundreds or hundreds of thousands of sites on the catalytic surface in order to be able to get good statistics, etc. So in practice, we never really solve the master equation, we instead simulate trajectories, stochastic realizations of the master equation, and we sample these in order to get the statistics, to estimate the observables that are of interest for our particular problem. Observables like the catalytic activity, the selectivity, the average coverage of species on the catalytic surface, etc. So to do this generation of these stochastic trajectories and the sampling, we use, of course, the Kinetic Monte Carlo method. So the Kinetic Monte Carlo algorithm follows conceptually the description that I mentioned a few slides ago. So basically, we start by defining our simulation. So defining the lattice type, defining the reaction events that may happen, the adsorbate interaction energies, etc. Then we initialize all the data structures and we populate the lattice. We create a queue of all the microscopic processes that may happen on the lattice. Remember, for that we have to first of all detect what kind of events will happen on the surface, like adsorptions, desorptions. So adsorptions on empty sites, desorptions from occupied sites, diffusion events potentially from an occupied site to an unoccupied site, etc. And for each one of these events, we have to generate some random numbers, exponentially distributed random numbers, which give us the time in which a reaction may happen. So after all these preparatory operations, we enter a loop. This is the main Kinetic Monte Carlo loop, in which the first step is to advance the time to that of the first process, the first elementary event to occur. We want to report the observables and then execute the process. So when I say report the observables, we may want to write in the output files the number of adsorbates that we have on the surface, the lattice state, the counts of reactions that have happened, etc. These are the things that we typically report. Then we execute this process, right? The process that was decided in this first step. So we change the state of the lattice, right? So we update the state. So if it's let's say an adsorption process, then we would place the adsorbate on the site on which adsorption is going to happen. Then we have to update the event queue. So first of all, we have to get rid of the adsorption event, right? Because we just executed it. Then we would have to detect the desorption event that may happen from that site, which is now occupied. And we may also detect other events like diffusional hopping from that site to neighboring empty sites. So this way we update our queue and then we go back. We ask, of course, did we reach the final simulation time? Yes or no. If yes, we terminate. If we haven't reached it yet, again, we go to this first step of the loop. So we find the first process to occur and we advance the time to that of the first process. We report the observables, execute the process, do the updates, etc. and so on and so forth. So this is how the Kinetic Monte Carlo algorithm operates conceptually. And of course, if you want to code this, you would have to certainly deal with some implementation issues about how to represent your lattice, your events, how to detect and update, etc. So some of these things we're going to discuss in the final part of this lecture when we deal with some advanced topics on Kinetic Monte Carlo as well. Typical Kinetic Monte Carlo output is shown here for a very simple reaction by which oxygen from the gas phase comes over to the surface via dissociative adsorption, and then CO comes over from the gas phase to the surface via non-dissociative adsorption, and then these two adsorbates can react and give off CO2 in the gas phase. So here we plot the coverages of oxygen and CO, oxygen with red, CO with blue. And we see that there are some fluctuations, of course, because of the stochastic nature of the simulation. This little movie here shows the different configurations as they are sampled. So this is our lattice. It's a 6-fold lattice. Each site has 6 neighbors. So some of these sites are occupied by oxygen. Some other sites are occupied by CO. So the red is the oxygen, the blue is the CO. And we can also monitor the number of CO2 molecules produced per time. So the line that we see here has a slope that allows us to calculate the turnover frequency in terms of number of CO2 molecules produced per unit time per site. So we can normalize with respect to the number of sites and find the turnover frequency. Note that, of course, we have a continuous production of CO2 molecules in this case because the system is far from equilibrium. So we assume for these simulations that the concentration of the composition of the gas phase does not change. So we may have 50-50 CO and oxygen in the gas phase, and the composition is kept constant for this simulation. So we will continuously have COs and oxygens coming into the surface, getting converted, and leaving us CO2 from the surface. Finally, in this plot here, we can see the event frequencies per site for every reaction event that is taken into account in our simulation framework. So we have CO oxidation, where CO and oxygen react and give off CO2 in the gas phase. We have some diffusion events for CO and oxygen, and then we have some adsorption and desorption events. So the forward events are with the red-orange color, and the reverse events are with blue. And we see that these events are quasi-equilibrated. So the forward and the reverse event rates are the same. So this is indicative of quasi-equilibrated events. Whereas this CO oxidation event is the rate limiting step for our particular process. So this is non-quasi-equilibrated event, and it has the smallest rate out of all of these. So it's the rate limiting step. So as homework, I would like you to try to code a simple Kinetic Monte Carlo program. So as a simple example, you can code a system with adsorption-desorption elementary events for just one adsorbate, single site type, very simple stuff. You can, to avoid too much complexity, you can use a two-dimensional matrix to capture your lattice. And then if you initialize your matrix with zeros, this means completely empty lattice. And then if you have 1 at an element of your matrix, then this means that this site that corresponds to that element is occupied. So you can have a simple set of rules, adsorption and desorption. And when you code your Kinetic Monte Carlo, try to compare your results with the analytical expression from the Langmuir isotherm. So you can try, like I said, a very simple example without lateral interactions, just adsorption, desorption, and your results should be in line with the Langmuir isotherm that we discussed in the previous lecture. So this would give you a way to validate your code. This brings us to the end of the second part, the simulations of reactions on spatially extended systems at the mesoscopic scale, and we're going to move on to the last part, which is a bit more advanced. It touches upon topics on the accurate modeling of catalytic surface reactions in which we may have these sources of complexity that we need to address.